Okay, so the aim of the talk is to challenge the conventional view about the strong CP problem by showing that if you take the infinite four-dimensional volume limit in a careful manner, then you get that QCD does not violate CP, regardless of the value of the theta angle. And why this is new? Because, yeah, this would mean that there's no need to tune the theta angle to explain the absence of CP violations in the strong interactions, as so far confirmed by experiments. The plan of the talk is to review the fundamentals of the strong CP problem, then I'll move on to computations of correlation functions using instanton methods, and then I will try to obtain these results not using instantons in order if people are not satisfied with the dilute instanton gas, and then I will, if I have time, make some comments about finite volumes and subvolumes. So let's go to the first part, fundamentals of the strong CP problem. So the action of QCD has the, well, the term coming from the non-abelian field strength, and it has terms from number of NF Dirac flavors with a Dirac operator and masses where, in principle, one can have complex phases in the fermion masses. Could be arbitrary. In order to get a real Lagrangian, these masses have to enter with opposite phases for the left-handed and the right-handed part. And now there's an additional term which involves the field strength and its dual, and this term can be seen to be a total derivative. So it then picks up contributions from the boundary of spacetime. And these boundary terms, they never contribute in perturbation theory. So this means that if this parameter has any effect, it will come from non-perturbative contributions. The interesting thing about this term is that this is CP odd. So under CP, the spatial components and the temporal components of the gauge field transform with opposite signs, and with the Leibniz tensor, this implies that the term changes sign under CP. So this, in principle, naively, you expect that this term would imply CP violation. And this would show up in observables such as the electric dipole moment of the neutron. But experiments have only been able to put very low bounds and have not seen an electric dipole moment of the neutron. And so this is called the strong CP problem. Thus, this means that theta is small. This is not exactly the best formulation of the strong CP problem, but okay. I'll come to that later. So does the fact that when one has a CP odd phase automatically imply CP violation? No. In order to have CP violation, you need interference between different contributions to amplitudes. And let's just take an example, process involving some particles A going to particles B, and some amplitude square, which will have some, let's say, tree-level contribution, for example, and some loop corrections with some complex numbers C0 and C1. Let's consider the CP conjugate processes in which I change particles by antiparticles, and then the amplitude square now involves, is a similar form, but involves the complex conjugates of some coefficients. And then for CP violation would mean that the rate of the process minus the rate of the conjugate process is non-zero. And if you just expand this, you get a contribution like this. And this means that in order to have a non-zero contribution here, we need that the phases of this complex of C1 and C0 are misaligned. I mean, C0, C1, or just that the phases do not cancel. And okay, so we have in the QCD Lagrangian, we have two types of phases. The phases from the fermion mass terms here, and we have then possibility that you have phases coming from theta. Why do we have phases coming from theta? Because, okay, at least in the Euclidean action, this comes in the path integral as exponential of I theta times some integer number, as we will see later. And then this means we have two types of phases which could interfere, and you would naively expect CP violation. So what we're going to do is, in this talk, we want to compute correlation functions for fermions. And we want to see if we have contributions from two types of phases, the phases of the fermion masses, or the phases coming from theta. If we have both types of phases, there's CP violation, and if not, there's not. And so we are now building a machinery to compute correlation functions. So we will use path integral methods. So for a path integral, one starts normally with a transition amplitude from a Heisenberg picture eigenstate of the field operator into another one. And then, okay, we know from well, our classes of quantum theory, that this is a path integral with over an interval t and with boundary conditions for the fields set by these initial and final conditions for the field. But I can have another representation by inserting the identity, the spectral decomposition of the identity in terms of eigenstates of the Hamiltonian, and I get a form of this. But I want to isolate the vacuum contribution here, and in order to, the vacuum contribution would be only when I have only the zero term here. And a way to do it in principle is we take the time to infinity, and then this means that the contribution from n non-zero are exponential, are infinitely suppressed with respect to the vacuum contribution. And so I get my vacuum transition, my vacuum expectation values from a path integral over an infinite dimensional, an infinitely long time direction. If one wanted to recover the amplitude for a finite time interval, it's more complicated. One would need to know the wave function of the vacuum. And okay, I would start directly now from the vacuum, and then I would insert the identity expressed as a continuum version of this discrete in terms of the spectral decomposition of the identity in terms of eigenstates of Heisenberg picture field operators, and for the final and the initial conditions. And then I have to, okay, here I had a sum, I need to do some path integration for Heisenberg picture fields. And then here I have the usual path integral, but then I have to convolute the usual path integral with these vacuum wave functionals. So it's a projection of the vacuum state with eigenstates of the field operators. So in order to do this properly, it's very complicated. You have to do all this machinery. It's just much easier to just take t to infinity, and then you directly get the vacuum amplitude. Moreover, if one wants to restrict the path integral to a finite for the volume, I would need to somehow start from this and integrate out fluctuations in the complement and try to end up with a finite volume path integral. All right, so as I said, the effects of the theta phase, of the theta angle, have to be non-perturbative. So within this path integral, I have to compute non-perturbative corrections. So we will do it in the Euclidean path integral, although in our work, we have an understanding how to do it also in Minkowski. But this is out of the scope of the talk. So I have with my partition function of QCD this path integral over the gauge fields and the fermion fields. I do a big rotation to Euclidean spacetime, and then I end up with e to the minus Euclidean action. And the idea is to do semi-classical expansions of this path integral around extremal configurations of finite action and perturbations about them. And in the following, I will omit making the Euclidean explicit. It will be assumed that everything is Euclidean. So what is this semi-classical expansion? Let's just a cartoon picture of my infinite dimensional field space, and I have the Euclidean action, and then I will have some saddle points, which or some critical points of the Euclidean action, and then I have some directions in field space in which the Euclidean action grows, and then I can do a Gaussian approximation around the integrations about this. And then I will have some directions in which the Euclidean action is not changing, and these are called the Zeromode directions. So when I do the path integration, I can do a Gaussian approximation for the non-zero modes, and then I have to integrate over the lines of the zero modes. Okay, so of course, I want to expand my integral around saddle point configurations and perturbations around them. And the perturbations that saddle points that will contribute have to have finite Euclidean action, because they enter the path integral as exponential of minus the Euclidean action. If it were infinite, they wouldn't contribute. In order to have finite action, the action is an integral over spacetime, so the integrand has to go to 0 at infinity, right? When does the integrand go to 0 at infinity? When my configurations are gauge transformations of 0. So they can be 0 or gauge transformations, so pure gauge configurations. So this means that I have my R4, and then at infinity, let's for example take a sphere at infinity, my configurations have to approach pure gauge. A pure gauge is just a pure gauge transformation of 0 of this form. So then I get a mapping from the sphere at infinity to the gauge group, and these are classified by homotopic classes. So, I mean, I fix the radius r, and then I have the 3 sphere parameterized by angles, and then I get a map from the 3 sphere to the group. And these are classified by homotopic classes, which are the different ways you can wrap the gauge group over the 3-dimensional spheres, which are not connected by continuous deformation. Now, I talked about a fixed R, but if you have a continuous R dependence and these homotopic classes are invariant under continuous deformation, as long as the dependence on R is continuous, there's a unique class defined for some given field configuration. This means that all finite action configurations fall into homotopic classes characterized by integer numbers. Why do I tell this? Because this integer number actually is related to the theta term of the QCD action. So in the Euclidean version of the action, the theta term had this field strength in its dual, and it turns out that this is I theta times an integer, which is this integer characterizing the homotopy class. And this integer can be connected through the Atiyah-Singer's index theorem to the zeromodes of the Dirac operator in the background of the homotopy class. So the number of right-handed zeromodes of D slash, meaning satisfying D slash times right-handed spinor equals 0, minus the number of left-handed zeromodes. And this will be used later. Okay. I talked about now the restrictions that having a finite action saddle point demand. And this leads to integer topological charge. Now, what about fluctuations around these saddle points? And at least in the Gaussian approximation, one can show that even if the fluctuations have infinite action, they are like plane waves, you still have integer topological charge. So this means that our whole partition function, I express it as a sum of path integrations around perturbations around the different saddle points. But as both the saddle points and the perturbations are classified into topological classes, I have my partition function as a sum over integer topological classes of the partition functions within each class. And within each class, I have a path integration along this. And as we saw before, the theta angle enters in the Euclidean action as a phase like this. And now you can see why theta is called a theta angle, because if I change theta by 2 pi, then the path integration remains invariant. Okay, so the big point that I want to make here is I've argued that my path integral is classified into topological classes, but in order to do this, I had to make for the infinite volume limit, because only by requiring finite action at an infinite spacetime, I arrive to the conclusion that you have integer topological classes. This means if I have to sum over topological sectors, I have to do it once I know that there are topological sectors. So after taking the 4-dimensional limit going to 0. If one wanted to, the question is, are there topological sectors in a finite subvolume? It's not so easy. Again, if you wanted to restrict to a finite time interval for the subvolume, one needs to do more work in the path integral, either knowing the vacuum wave functional or integrating fluctuations in the volume complement. And if you have finite periodic spacetime, for example, like torus as used, Euclidean torus as used in the lattice, then you get topological classification, but it's not the reason why you get it in Minkowski. Okay, so we will now let's present Weinberg's argument also about how the theta angle can appear from a different perspective, which is cluster decomposition. Forget now that there's a theta angle in the Lagrangian. So assume that there's no theta angle in the Lagrangian. But assume that I still argue that there's a sum over topological sectors. And I want to weight these topological sectors in a way. So I could write the expectation value of an observable O in a volume omega as a sum over path integrations on the different sectors weighed by some weight factors and then divided by the partition function, by the total partition function. So let's imagine that my operator O has support in a local spacetime volume omega 1, and then I can factorize the integral over the whole volume in an integral over volume 1, where you get then, since O1 only has support in the volume 1, you get it in this path integration, and then the integration over the rest of the volume. Now, I assume that my topological charge is like a surface flux. So the total surface flux, because I said that the topological term in action is a total derivative, so then it's a surface flux. So the total surface flux is the sum of the fluxes over the surfaces over the two volumes. So I can express it as the flux in volume 1 and the flux in volume 2. And the same for the partition function. And now, if physics is local, this means that in order to compute the expectation value of O1, I shouldn't care about what happens in the volume 2, right? So then I should have cancellations. And this cancellation can happen if the weights of the weight of the sum is the product of the weights, because then these sums over n factorize, and then I can just cancel in numerator and denominator, the sum over n2, and then I end up only with contributions from O1. And the point is that the solution to these weights, one solution is just e to the I delta n theta, which is the weight, the term we had in the Lagrangian from before. All right, so we've talked a lot about theta. The question is this angle physical? And here one has to be a bit careful, because it changes under field redefinitions, and physical observables cannot change under physical redefinitions. So we know that the anomaly of the chiral current gives a divergence of the chiral current, which has, a classical piece due to the explicit breaking of chiral symmetry by mass terms, and then a quantum piece which actually involves, the topological charge density. So if I do a chiral transformation of the fields, e to the I beta gamma phi, then my partition function in terms of the angle theta and the phases of the fermion masses is not invariant. So my fermion masses change because classically mass terms are not invariant. And then due to the anomaly, it can be seen that theta changes by minus 2 times the number of flavors times the parameter of the transformation. So it's not a symmetry because the partition function is not invariant. But now let's imagine I consider theta angle of the phases as expectation values of some background field. So I can cook up, if I were to transform back the theta angle and the fermion masses with a compensating transformation, then I would get a symmetry, because if I add now 2 times NF beta back, I get theta, and similarly for the fermion masses. So then I know that formally the partition function has to be invariant under these changes. Okay, and this is a spurion symmetry. It's not really a symmetry because I'm relating, I'm changing the parameters. But a point is that physical quantities that appear should be invariant under these field redefinitions. So there's a quantity which is this theta bar, which is theta plus alpha, where it is the sum of all the arguments of the mass matrices. And this should appear in observables, in CP-violating observables. So the real strong CP problem is, why is this specific combination, which is physical, small? Okay, so I said that theta should appear in non-perturbative effects. So what is known about non-perturbative effects in QCD? So if you integrate the anomaly equation that I had before, it predicts that the change of chiral charge under an infinite time interval is 2 times the number of flavors times the topological charge in a given background. And then this predicts that there are interactions that violate chiral charge by this amount. And this can be recovered from contributions to the path integral around saddle points, as we said before. And these saddle points of the Euclidean action QCD are called instantons. And as Toft showed, one can get some effective vertices with violate chiral charge by these units. For example, if I have topological charge equals 1, I would violate chiral charge by 2 NF units. And here I have, for example, 3 flavors. And then I have chiral charge minus 1 from the left-handed. And I end up with chiral charge plus 3, so I violate by 6 units as expected. And similarly for topological charge minus 1. Okay, so in principle, these are computed by computing correlation functions in the backgrounds of instantons. And one can cook up an effective Lagrangian that gives the same answers. And in this effective Lagrangian, actually, it has a determinant structure because I get a product of fermion bilinears of all the flavors in the theory. And the question is, what is the phase? The crucial point is, what is the phase of this effective Lagrangian? Because, I mean, the phase has to comply with my spurious symmetry. So this means that this effective Lagrangian has to be invariant under my spurious symmetry. And for example, here it's two Fermi bilinears with PL. So this has chiral charge -2. So this means that this phase has to have chiral charge +2. There's two possibilities of chiral charge +2 NF, sorry, because I have a product of flavors. There's two possibilities, either theta, because we saw here that I changed by 2NF, or actually it can be -alpha, because it transforms in the same way. And both options are perfectly compatible with the anomaly. And in this case, one gets CP violation because then here there's misalignment between the phases of the quark masses and the phase of the non-perturbative top vertex. But if my phase is given by the fermion mass phases, then there will be no CP violation because there's alignment and I can do a Filbert definition and I get rid of all the phases. So how this would appear in the chiral Lagrangian, because this was effective interaction for vortex. So at low energies, QCD becomes non-perturbative, and of course, it's difficult to do anything with this. And one can work, for example, with a chiral Lagrangian, which includes the pion fields. And in fact, the top vertex that we saw before that had a determinant structure on flavors shows up in the chiral Lagrangian as a determinant term of this unitary matrix U, which essentially can be thought as incorporating the fermion bilinears. And yeah, is related to nonlinear representation of the Goldstones of the broken flavor symmetries. And again, here, this chiral Lagrangian should be invariant under the spurious symmetry. Under the spurious symmetry, U transforms with charge +2. And playing the same game, now I have, again, two options. Either this phase is aligned with theta, or either this phase is aligned with alpha. And in one case, I get this phase with theta is the usual option, which has been assumed in estimates of the neutron dipole moment, for example, using chiral perturbation theory, and leads to CP violation, but with this phase, there will be no CP violation. So how do we know which phase? So the chiral Lagrangian is an effective theory. So the idea is you have to match it to UV computation. So the idea is compute things in QCD and match, identify the phase. We only know of one computation, which is Toft's, in his paper of how instanton solves the U1 problem. And he, using the dilute instanton gas, he concluded a phase theta. So CP violation. What we have done is we have also done the computation in the dilute instanton gas method, but with a different infinite volume limit, we get no CP violation. And in order to make sure, because many people are skeptical about the dilute instanton gas approximation, even though Toft used it, we also have an argument without using the dilute instanton gas. Okay, and just a comment. So in a regular gauge, the usual picture is in conflict with locality. And what do I mean with this? I mean that in a regular gauge, we saw that the theta terms in the path integration come from the boundary of spacetime. But if my physics is local, I shouldn't be sensitive to what happens in the boundary. And then somehow, intuitively, something is a bit weird. So what is the goal next? Is to identify the correct phase in the effective Lagrangian by estimating non-perturbative contributions to fermionic grid functions, keeping track of all the phases coming from theta, and the phases coming from the fermion masses. So first, using instantons, and second, just trying to constrain the partition function itself. So let's go to the instanton computations. So the naive picture, which is how I always thought it would go, imagine this box is spacetime, and imagine I want to compute a correlator with 3 left-handed fermions and 3 right-handed fermions, and these positions are the position in spacetime at which I'm evaluating my green function. So in the sector of topological charge 0, my propagators, I will get a product of 3 propagators, and this just, I get some phases aligned with the masses of the 3-level propagators, so I get a coefficient proportional to the sum of the fermion phases. And now in the topological sector 1, I will get some Toft vertex in one instanton contribution, And then I would get, since I have the phase in the path integral exponential of I delta n theta, delta n is 1, so I will get e to the I theta. And then I get determinant of the fermion fluctuations, which actually cancels alpha, and I will get e to the I theta. And the relative phase would be theta minus alpha, so theta plus alpha, or theta bar, which is the physical CP-violating angle invariant of Taylor definition. I would expect CP-violation. Why is it not so simple? It's not so simple because the topological charge can be delocalized. So even if I have a sector of topological charge 0, imagine that I can still have local non-perturbative fluctuations such that the topological charge in total is 0. But in small regions, I have approximate integer topological charge which is non-zero. So if, for example, I have a dilute gas of instantons and anti-instantons. Instantons have topological charge 1, anti-instantons have topological charge minus 1, and here the sum over instantons minus the anti-instantons is the total topological charge. So in my sector 0, I have equal number of instantons and instantons, but then I can have, again, if I have a correlator with localizing spacetime, I get contributions in which I don't get any instanton in the middle, and they look like the vacuum. But then I have contributions non-perturbative from instantons, but again, I also get the same result because delta n is 0, so I don't get any theta. So this means that perturbative and non-perturbative contributions within this sector are actually aligned. Similarly, for sectors with topological charge different than 0. Here, delta n equals 1. I have one more black dot than gray dot. But again, here, my total phase is just determined by e to the I delta n theta, so I get theta for both. This means that if I stay in a single topological sector, there's never CP violation because the contributions are aligned. So the CP violation only comes when interfering the sectors and summing over all the topological sectors. So let's summarize the strategy. So again, we evaluate the integral by identifying saddle points, integrating the fluctuations about saddle points, and summing over all the saddle points. And well, it can be done in Minkowski. The Euclidean is the usual, so let's focus on Euclidean. And how do I compute a fermionic green function? Let me consider a two-point function. So the partition functions and the two-point function is, okay, the propagator in the background of my gauge fields. But then I have to include the integral over the vacuum fluctuations, which are some gauge or fermionic determinants. I have to sum over all saddle points within each topological sector, and I have to sum over the topological sectors. So now I will summarize the main aspects of all these computations. So what is new? Yeah, we understand it in Minkowski as well, but this is a subject for another talk. We are very careful tracking all the dependence on the complex fermion masses, because usually people always assume you go to a basis in which the fermion masses are real, for example, and so on. And we want to track both theta and arbitrary fermion masses, just to make sure we are compatible with the Spurion symmetry. And then, again, this careful treatment of the summation over topological sectors versus the infinite volume limit, such that we only sum our topological sectors after taking the infinite volume limit. And of course, so all the techniques that we're using here are not new. So as you will see, the only thing that we depart from the usual literature is here. So what are the saddle points? Are these well-known instanton configurations as used by the PPST instanton and then used later by Toft. What do they look like? Essentially, they look like some localized function localized around a center which coordinates x0, so 4 coordinates. Then it has a size, which is called rho, which is arbitrary. And then it has some parameters related to where it's pointing in SU3. And then some coefficients. And these are known as the collective coordinates, which are arbitrary. So I have to, when I'm summing over instantons, I have to integrate over these collective coordinates. The next part is how do we estimate the fluctuation determinant? And I give you essentially the result. So, I mean, it's a dilute gas of the instantons. Most of space-time, you have no instanton around. It looks like a free operator, right? And then it's approximately, I just given my determinant of free operator. But then there's corrections near the instantons. And then I get, if I have n instantons, I get corrections due to the instantons. And if I have n bar instantons, I have corrections due to the anti-instantons, sorry. Mathematically, how could you argue it this way? One possibility is saying, okay, I define my determinant from a spectral decomposition. And you would get this if you assume that the continuum modes are the same as in the free operator. I mean, at least at high momenta, you wouldn't see the instantons. And then you have discrete modes coming near the centers of instanton and anti-instanton. So then you would automatically derive this.
This is common to your approach and
Sorry?
This is common to your approach and the previous one. Right?
At least this structure is done, for example, in computations of tunneling in scalar theories, not gauge, but this is just how Coleman argues that the bounces exponentiate. It's the same thing. So this is nothing extraordinary. What we have done now is being careful of the phases of these determinants. And actually, when you have complex fermion masses in the determinants, yeah, the operator is not Hermitian, but you can have complex eigenvalues. But we have shown in the additional material of the paper that, okay, so first, the ordinary determinant is real because the phases come in pairs due to related bichirality. And then the non-zero modes of the instantons and anti-instantons give also real contributions because they are coming in pairs as well. And the only complex phase comes from the zero modes. And why is this? Because, okay, if I have, for example, in an instanton background, I want to compute, if I have a zero mode which is annihilated by the Dirac operator, then I have an I just pick this piece, and then I have a phase e to the I alpha. And if I have left-handed zero mode, then I get, of course, this gives me 0, and then I get e to the I alpha gamma 5 acting on a left-handed is minus, so I get the opposite phases. So in order to get the total phase, I have to count the number of right-handed zero modes minus the number of left-handed zero modes. But the Atiyah index theorem tells me that this the number of right-handed zero modes minus the number of left-handed zero modes is the topological charge. But this topological charge is just n minus n bar, and then this fixes me the phase of the total fermion determinant. For gauge fluctuations, I play the same game. The difference here is that we have to, the integral along the directions in which you get the Euclidean action doesn't change. It's actually not Gaussian. So instead of a determinant in these directions, I get something else. But what you do is you trade the integration over these directions with an integration over these collective coordinates of the instanton. The center, the location of the center, and the integrations of the size and the rigid SU3 orientations. I just isolate the center because I will use it later. And then I have a Jacobian from my change of variables from the field directions to in terms of integration over these collective coordinates. And then I have a determinant prime of the non-zero modes. And for this, similar to the fermion case, we write a similar expression. And again, in this case, I have no phases. And I just get a parametrization in terms of the free determinant and some omega. And what does the propagator look like? Again, it looks far away from the instanton. It looks like the free propagators. And then near the centers of instantons and anti-instantons, I approximate it by spectral decomposition around the instantons and anti-instantons, which at least, I mean, argued by Schiffman, Weinstein, and Sakharov, if the masses are small, the contributions from the zero modes dominate. And of course, here, again, we are not the first ones to do this. Schiffman and Sakharov only consider this piece, but then Diakonov and Petrov actually also realized that there's continuum modes. So, and then to a correlation function, essentially, I have to assemble all the pieces. So I said I had the fermion propagator in the background, and I have all these, I have the classical axiom coming from the saddle points, and then I have all these fluctuation determinants and the phase from theta and the phase from the fermion determinant conspiring, and then I have I need to sum over all the instantons and anti-instantons, so I have a sum over n bar, and then I'm restricting now a topological sector n, so I restrict n minus n bar equals delta n, and I have to divide by permutations of instantons and anti-instantons that just give me the same result. All right, so now let's move on to the different pieces. So first, I do the integral over the translation collective coordinates. So if I have a propagator, as I wrote before, was the free piece plus contributions are on the anti-instantons and contributions are on the instantons. And now I do the integrations of the translational coordinates. So the free piece doesn't depend on the translational coordinates of the instantons, right? So I just get a factor of the space-time volume times the n plus n bar, because I have n plus n bar integrals. But now every term in the sum, the integral is only non-trivial for one of the instantons or anti-instantons. So I get Vt for every trivial integral, and then I get some overlap integral for the rest. So then I get Vt to the number of instanton plus anti-instantons minus 1, because it's the term, the integral is non-trivial. And then I get this structure for left-handed projectors here, because this is left-handed, I get this e to the minus I alpha in the denominator, and for the right-handed, I get e to the I alpha. And these h are essentially the integrals that are non-trivial, and which are integrals of the zero modes, and just we approximate them by the averaging over the rest of the collective coordinates. Just why do we do this? Because then the rest of the integrals factorize, as we'll see. Again, here, there's also nothing non-standard. So now I have done these green pieces. I want to do now this sort of dirty yellow. And then this is an overall factor which comes from the free determinants, but this is also appearing in the partition function itself, and it will cancel when I divide by the partition function. So let me ignore this for now. And the point is that under the approximations I've done before, the rest of everything factorizes, and I can do, I get these nice expressions, a sum over n bar, and actually with these overlap integrals, and it turns out that this sum can be done, and this sum just gives Bessel functions. Okay, and so from here to here is just exact. And doing analogous computations, one can just do, instead of the correlator, the whole partition function, and again one gets Bessel functions. Actually, this Bessel function structure has already been seen before by Lloyd, Boyle, and Smilga, but arguing differently. So now is the final part. We have to sum over the topological sectors and divide by the partition function. Okay, so I have my fermion correlator is what I computed before, fermion correlator in a topological sector delta n. And now I have to sum over the delta n's and divide by the partition function. But then, okay, so I first, delta n is only defined, it's an integer in the infinite volume limit. So first, I take the infinite spacetime volume limit, and then I extend the sum over the topological sectors to infinity. And the nice thing is that in the infinite volume limit, all the Bessel functions asymptotically tend to a common value. So whenever I see Bessel functions, I have to essentially do here in the numerator and this in the denominator. All the Bessel functions tend to a common value and they cancel out. And then I get a super simple result, which is just the free propagator and a correction with the overlap function, and now a phase determined by the fermion masses. And let's remember, the free propagator can be written in this form. So you see that here I have a phase determined by the fermion masses, and here I have exactly the same phase. So there's alignment, which means there's no CP violation. Of course, here I just computed a two-point function, but we can generalize this to n-point functions. And also in Euclidean and Minkowski. So my effective Lagrangian now, I do my correlators in QCD, and my effective Lagrangian, I would have these phases that are saturated by the angles of the fermion masses, and I conclude there's no CP violation. Where do things go differently? I mean, all the techniques we use are pretty standard. It's only in the last step, because I mean, this is the result I just gave you. But if I were to do first the sum of the topological sectors and then the infinite volume limit, again, the sum can be done, and one gets the standard result, which is just the theta phase. And then in this case, one has CP violation. So we have just used standard techniques. We understand the usual computation, and we get the same result as Toft, doing it the way he did it. But there's a subtlety, which is this ordering of limits. And if you think about how does one get a classification into integer topological sector of integer charge, we could only argue for it in the infinite space-time volume limit. So we think that this is the correct limit. And now let me move on. Okay, so this is instantons in the dilute instanton gas approximation. And
there is also minus sign, not just a change in phase, right?
Yeah. So I mean, yeah. So it would be theta plus maybe pi, or yeah.
And that would be the standard result.
Yes.
You
yes.
find a change of sign in the theta, but also
yeah.
Pi half, excuse me, pi phase.
Yes. So there's also a difference.
Doesn't make any difference.
Not for CP violation, yeah, because it's just a real thing. Okay, so now let me try to get the same an analogous result without using instantons. So then the strategy is to constrain the functional dependence on the partition function on its topological sector, on the volume, the topological charge, and the holomorphic fermion masses. And so the structure is that if I have my Lagrangian, now I write, remember before I had m e to the I alpha gamma 5, let me rewrite it in terms of some holomorphic masses, including the phase, in this way. So I get, as I said before, I had opposite phases for right-handed and left-handed, so I have a mass of the conjugate. But now, so the Lagrangian appears in the path integral as exponential of minus the Euclidean action, right? So if I take derivative of the partition function, for example, with respect to m, from the exponential, I drop a fermion bilinear psi bar pi right-handed projector psi, right? If I have e to the derivative of e to the minus this, then I get e to the minus this times this. But then I means that the derivative of the partition function with respect to m is a fermion correlator. And the derivative of the partition function with respect to the m star is also a fermion correlator with a left-handed projector. So the strategy now is, of course, this is not the most general correlator because it's at coincident points and integrated over. But if there are constant CP-odd phases, I would see them. The idea is I want to see what is the dependence of the partition function on the masses and take these derivatives and see what phases I get. And this is when I come back to the clustering of Weinberg that I introduced before. So remember before I argued that in the Weinberg argument of cluster decomposition that one can factorize the path integral. So in this path integration, one factorizes the total partition function, which, okay, I can isolate away the phase due to the theta angle. And then using the property that the topological charge was a flux, I can factorize it in partition functions of subvolume omega 1 and omega 2, and the phases from the theta angle. And since theta is arbitrary in principle, one arrives to some infinite number of constraints on the partition function. And we want to see if we can solve this infinite number of constraints on the partition function.
So there you've already taken the infinite volume, right?
In principle, for the total volume, yes. Yeah. And there's a subtlety here. Once you do this, it's, I mean, Weinberg does this in this book, and he doesn't mention anything. But once you do this, in principle, it's not strictly true that then delta n1 and delta n2 are integers. But at least, for example, if you consider omega 1 is infinite and omega 2 is a finite subset, one would hope that you're only making an error in a compact boundary of spacetime in the whole path integration, and this should be a good approximation. So let me accept it by faith, but yes, this is a caveat. And let me assume now I want to isolate all complex phases in the partition functions. So I have already isolated the phase depending on theta. I want to isolate the phase depending on the fermion masses. Now let me assume that the since these partition functions have the structure, for example, of fluctuation determinants, let me assume that this phase is as it was at one loop around instantons, is fixed by the index theorem. So then the phase is delta n times the sum of fermion phases. So then I have my partition function as some phase coming from the fermion masses and some real function. And this real function, substituting this ansatz, has to satisfy this infinite number of relations. And I want to see if I find a solution. So first, one can do some argument on parity. Parity changes the sign of delta n and alpha. But now these G delta n's don't know about the fermion phases because I've separated them. So they are the result when the fermions are 0. But in that case, I have invariance under parity. This means that, since there's invariance in the parity, G with topological charge delta n should be the same as minus delta n. And now in the relation, now formally I can substitute volume 0, and then I get this recursion, this relation, and it can be solved by, if you just put on here delta, the Kronecker delta, then this relation is solved. And these two relations motivate an ansatz that, okay, first I have some function that only depends on the sign of delta n. And in order to ensure that when I substitute volume 0, I only get non-zero result for delta n equals 0, then I put a space-time volume to the delta n. Because then I get 1 for delta n equals 0, so non-zero, but I get 0 for all the others. So this is just an ansatz. Now I plug this ansatz into my infinite conditions here, and if I assume analyticity in omega, there's a unique solution. And this unique solution actually is, surprise, a Bessel function. So this means putting back all the other phases that I isolated before, I get essentially the same structure as I had with the dilute instanton gas, but without using instantons. And now I wanted to get correlators of fermions, and I have to know how did the fermion masses enter here. So the G's were real. This means that the G's gave me this Bessel function. They can only depend on products of masses times their conjugates, because otherwise I would get phases. And then alpha is essentially a sum over fermion phases, but the fermion phases can be expressed in terms of log of m over m star. So now I have my partition function as a function of the complex masses, and then I can get the fermion correlators by taking derivatives with respect to the masses. And I get these results in terms of Bessel functions. And just a check, these results comply with the Spurion-Chiral symmetry, because, for example, this must have chiral charge plus 2, right? Because it's right-handed. But then, if you see the Spurion charge assignments that I had before, 1 over m has chiral charge plus 2, and m star has chiral charge plus 2. So all these satisfy the anomaly requirements. And now I just have to sum over topological sectors. And again, I do taking the infinite volume limit first, and then summing over topological sectors to infinity. And the result one gets is that the total phase, I mean, this is just the total contribution, not separating tree level or non-perturbative, it's just the total. And the total is just aligned with the phase is determined singly by the fermion masses in a way compatible with the Spurion symmetry. So again, I conclude the same as before, no CP violation. Do I have some time, or shall I conclude?
5 minutes, I guess.
Okay, so let me then come to a last part. So as before, I talked about doing things in infinite space-time volume, and I said if you want to get correlators in terms of an integration in a finite space-time volume, you should be careful and integrate out the fluctuations in the complement volume. So this is what I want to do now. So before, remember, I had this expression for an operator in some, with some support in some volume. This is the infinite volume, and I had, this expression as before. And now, assuming that this operator has only support in some volume omega 1, I had this factorization that I had before. So this is what we saw already. But now, I mean, what are these path integrations on the volume 2? This is just the partition function, because it's just the path integral in the vacuum. Then I substitute the results I get for the partition function in terms of Bessel functions. And now, if I am interested in a finite subvolume omega 1, then omega 2 is infinite, right? And then I take the infinite volume limit for omega 2, and as I said before, the Bessel functions tend to a common limit, and then I get a nice cancellation of Bessel functions, and I end up with my expectation value of an operator with local support expressed in terms of a path integration in omega 1 in the local finite volume, but theta has disappeared. Theta just cancels. So the theta angle is not there. And actually, I have some extra, I mean, this is not my naive reduction of the path integral. I mean, if I was just naive, I would just have d phi O1 e to the minus s gamma 1. I have some extra phases. And these extra phases come from the integration on the complement and actually cancel the phases of the fermionic determinant, and one ends up essentially with no complex phases in here, and there's no CP violation. So, I mean, essentially, this is our way of saying that if one computes expectation value in terms of a path integration in a finite subvolume, as you would do in a lattice, then it doesn't make sense to put the theta angle there because it drops out of the computation. Yeah, this is essentially what I saw before. There's a path integration over the subvolume 1, but it has some extra phases. There's no theta, and these extra phases can be seen to cancel the phases of the fermionic determinants, and we recover the same results as before. And I think then I can conclude here. I'll say that QCD with an arbitrary theta angle does not predict CP violation when the sum over topological sectors is performed after taking the infinite volume limit. And this infinite volume limit, this ordering of limit is, we believe, the correct one because the topological classification is only enforced in the infinite volume limit. Otherwise, you don't have necessarily a classification into topological sectors of integer topological charge. And actually, with this limit, the physical predictions do not depend on whether one sums over topological sectors or not. And then if I have local observables with support in a finite subvolume, I can recover them with a path integration in a finite volume, but in this case without any theta dependence. And I still conclude that there's no CP violation. And with this, I'll finish, and thank you for your attention.
If I understand correctly, your second statement and the fourth statement there are equivalent, right? Or not? If you're saying that you cannot enforce topological classification in finite volume, that's what I'm saying, right?
Sorry?
What I'm saying is that your second statement there is the same as the fourth statement, right? If you're saying that you cannot, in finite volume, you cannot enforce the topological classification.
I think it's related, but I mean, in this case, to arrive this, we have this caveat of the, in the clustering relations, we have done an approximation that, in principle, you would have non-integer topological charge, and we are approximating it as integers in that case. But, I mean, our approach here is, okay, we want to get the infinite boundary right. And then for a finite boundary, we allow ourselves to make an error in the only including integer topological charge. But of course, if you have the whole path integral, making an error in essentially in a region of measure 0 should be better than doing it in the infinite boundary. So this is a bit how we understand it.
This issue of the why you need the infinite volume to get the topological charges, that's I mean,
because the requirement defining the, sorry, yes?
You have a question that is pointing in. I have a question. In the former calculation by Topological using instanton, what was his argument to take the limit?
No, I mean, he didn't think that the limits didn't commute, and he just saw a double sum. I mean, he expressed the sum over topological sectors delta n and it just did it directly for finite volume, and then you get a series that looks like it's easy to compute, an exponential, and it just didn't realize that this limit didn't commute. And the reasoning.
So Toff was assuming that topological sectors are well-defined finite volume.
Yeah, so formally he has expressions of some product of determinants that are in principle computed at finite volume. And
this is what I kind of get lost, because you're talking about homotopic groups, homotopic classes of SU3 on SU. Right?
Yes. The boundary of space-time, yeah.
But the sphere is non-trivial topologically at any volume, right? Or no? That's what I'm saying. So I would see that you have different. The homotopic class doesn't change by expanding or contracting.
Yeah, but you only need that your gauge fields approach pure gauge configurations at R when you take this sphere at infinity. Because you want finite action. I mean,
that's what I did.
That's the crucial point. So to have finite action is an integral over the whole space-time. To have an integral that is convergent, you need the integrand to go to 0 at infinity, otherwise.
So the other way you would be assuming that the gauge fields are pure gauge
exactly.
For all possible boundaries.
Or at least,
yeah. But you don't have to do that.
No, exactly. So we're not imposing, we're imposing it by necessity, not by choice. I mean, imposing.
So that's not a choice. That's what I see what you do. So in finite volume, you don't need to have the pure gauge configurations in the boundary, and then you still have a convergent partition function.
Exactly.
Okay, I see. That was the point that I would have.
Okay. Thanks for the question. Yeah.
So the statement is that the community has chosen to have the CP problem for very long.
Well, I guess normally in physics we're assumed to analyticity in many cases, and you don't realize that some limits don't commute because, you just see a series which looks like an exponential, and then you resum it to an exponential. But the series is formal because it includes factors of volume that then is in principle formally infinity. So then you are doing manipulations of course, all that we are doing for a mathematician is probably not okay. But I would say that our way of proceeding is at least equally rigorous to the standard picture. We would say it's a bit more rigorous because of this argument. But then, if you are skeptical of our result, you should definitely be skeptical about the usual result because,
That's something that one can check in the lattice, no? When you go to the infinity volume, and so far they have fluctuations.
Yeah, but you can never go to infinite volume in the lattice.
Try to go and they see the behaviors. Right now there is a fluctuation of theta vacuum when you go to the infinity volume. So.
Well, what do you mean? Are you talking about topological susceptibility?
Yes.
Okay. Yeah, but for example, even in our case, I can define an observable, local observable, defined as the topological susceptibility, defining as the integral of FF dual over a finite subvolume. Okay? And if I play this thing, we still get, even though there's no theta, topological charge locally can still fluctuate. And I would still get a non-zero topological charge. So in a finite subvolume, as I said, the topological charge can be delocalized. And then I could fix my topological charge to be 0, but in a finite subvolume, I can still fluctuate. So I can still have, regardless of what happens in the boundary infinitely far away. So we still, even with our arguments, we still expect, and we comment on this in our paper, that at finite subvolumes, there's a non-zero topological susceptibility. The issue is that you cannot relate it to derivatives of the partition function with respect to theta. I mean, the usual argument that the topological susceptibility is related to CP-violation is because formally, if you have the Euclidean partition functions with theta, if you take the derivative of theta, you drop FF dual in the partition function, and then essentially, if you take the second derivative, you get a topological susceptibility.
I should ask whether there are any questions online. Give me a second, since there is one.
It's related to the previous one.
Okay, then Angel.
Yes. The mass dependence of the topological susceptibility will be different.
Sorry?
The fermion mass dependence of the topological susceptibility will be different in your approach, right?
Why?
You have dependent on required mass in your case.
Yeah, you have this alignment.
So this is something that the lattice can be checked as well against the Carol limit, for instance, or close to the Carol limit. This is something that is very important because the mass dependence of the topological susceptibility.
I mean, we still get that we still get that the topological susceptibility is proportional to the fermion masses.
Yeah, but not only proportional, the functional dependence to the mass. I mean, you can change the mass and set the lattice if it corresponds to your approach.
Okay, okay.
So that's something that can be tested.
Okay.
But still they are far away from the They are far away still to achieving that.
Okay, okay, I see.
We have a question online now. Paul Hoyer, please. Let's see if we hear you.
Yes, hi. Paul Hoyer. Very nice talk, and of course very great. So, could you tell what, if any, reactions you have had from people and what they criticize or accept of your analysis?
Okay, so now we come to the social effects.
Yeah. So the reaction is, of course, super strong skepticism, and so the usual reactions that we get is you cannot trust the dilute instanton gas. That's why we have an argument which doesn't use the dilute instanton gas. Then we had questions about the topological susceptibility, because of course in the lattice people measure a non-zero topological susceptibility, and this is connected to Jacobo's question. And our response to this is that the topological susceptibility is an expectation value of an operator which involves some space-time integrals. And whether you restrict the space-time integral to a finite subvolume or the full infinite volume, it's a different operator. And then when we restrict this integration over a finite subvolume, and we use these arguments before, yeah, we still predict a non-zero topological susceptibility, and so we would agree with the lattice there. People were criticizing whether we get a non-zero value of the eta prime mass or not in this approach, but I mean, we still get top vertices. In the Carol Lagrangian, we still have this determinant term, and even with this phase aligned, we still checked, we get a non-zero value of the eta prime mass. And actually, this non-zero value of the eta prime mass is proportional to the topological susceptibility in finite subvolumes. So it seems all to check. We've also had criticisms regarding, there's some arguments by Schiffman. Let me go to some backup. Okay. There's some arguments by Schiffman and collaborators saying that, okay, so they have the partition function and they do assume analyticity in theta, and they do some theta expansions within the path integral. They arrive to an expression like delta, the expectation value of the topological charge divided by the volume, is proportional to the topological susceptibility in the presence of theta. And so they use this to argue that whenever you have some non-zero topological susceptibility and non-zero theta, you have CP violation, because then they connect non-zero expectation value of delta n to CP violation, okay? And our answer to that is that, I mean, these manipulations are obtained by doing a Taylor expansion in theta of the partition function, but in our limiting procedure, actually the partition function becomes non-analytic in theta, and then yeah, doing the expansion within the path integral wouldn't be allowed. Yeah, and then, but regarding, I mean, the crucial point in the end for us, it's quite simple. It's just this ordering of limits. And we still haven't heard any argument saying, okay, this ordering limit is actually wrong. So most of the arguments seem to go a bit tangentially, saying how our results fit to other results in the literature. Also, okay, some comments about.
So you're saying that this expansion is forbidden?
Yeah, because I mean it's non-analytic.
You have assumed that it's analytic, no? To disperse everything.
I assume that it was analytic in the space-time volume, not in theta. Yeah, yeah. And of course, the partition function is not observable. Only the correlators where you divide by the partition function, and so yeah. Another comments that we got, well, of course, is the, I mean, there's people have estimated the electric dipole moment of the neutron without using instantons, for example, in chiral perturbation theory. And regarding chiral perturbation theory, our answer is that it depends on this phase that you put in the top term, and we have redone the calculation, and when we put the phase aligned with the Fermi masses, then in the Carl Lagrangian adding the neutron and proton fields, then you don't get CP violation interactions between neutron and pions, and so you don't get any dipole moment for the neutron. But Cruz et al. Didn't use directly the Carl Lagrangian. They used an effective Hamiltonian derived by Balluni and used by Veneziano et al. And for this, I have also some comment. So Balluni et al. Used some CP-violating Lagrangian, and the rationale is, okay, they say, okay, I have my Lagrangian of Fermi masses, and then I allow myself to do some field redefinitions. And they say that the correct way to get the CP-violating contribution to the effective Lagrangian is to find the field redefinitions which minimize the expectation value of this Carl Lagrangian. And then they get a CP-violating Lagrangian which involves a phase aligned with theta. But if you look at the derivation, there's a hidden assumption. And the hidden assumption, I mean, here you have to take expectation value. While they allow these field redefinitions, they still assume all the time that the fermion condensate has a phase aligned with theta. And okay, in Balluni's paper, if you go, he doesn't have a theta, he has 0 of pi. Why? Because he has started from a field redefinition in which he has put all the dependence on theta on the quark masses. But the argument is that there's an assumption of the phase of the fermion condensate, while in principle this assumption is not guaranteed. And if you do have the Carl Lagrangian, do I have the Carl Lagrangian? Yeah. If you have the Carl Lagrangian with the, okay, let's keep the phase arbitrary, you can actually derive the phase of the fermion condensate because, I mean, you have a potential for, let's assume that my expectation value of the field containing the pions is diagonal and has some phases, right? And these are essentially, since this is related to bilinears of fermions, this would be the phases of the condensates. And by solving minimizing the Carl Lagrangian on this background, one gets phases, so the phi's, which are actually of this form. And then, as you see, if psi equals theta, then, yeah, you do have a part of the phase of the condensate aligned with theta, and then Balluni's effective Lagrangian would hold. But if psi equals minus alpha, which is minus alpha u, minus alpha d, minus alpha s, actually the phase is 0.
But what happens at higher orders?
Huh?
What happens if you go to higher orders, which are not proportional to the determinant of u, which involves u minus u less, whatever? I mean, then that's not really one.
Well, but it's neither true for us, neither true for Balluni. So then you cannot trust any of them.
Okay, I think the question is sufficiently answered.
Yes.
Thank you.
And since the time is well past, I think we'll say goodbye to everybody. Thanks for attending this seminar.
Yeah.